we have seen quite a few different organic reactions already. The challenge of synthesis lies in combining these different transformations into a logical sequence to build molecules with more complex structures and more useful properties. We have seen simple acid-base reactions, like the deprotonation of phenol shown here, and learned to represent the movement of electrons using curly arrows. We've heard about nucleophiles and electrophiles and how they interact. We've seen that alkenes undergo addition reactions with electrophiles, like this hydrobromination reaction over 2 steps via a carbocation intermediate. In contrast, aromatic compounds like benzene react with electrophiles in a substitution reaction, which retains aromaticity in the product. Alkyl halides like the secondary alkyl bromide will undergo substitution reactions with a nucleophile like cyanide and various other nucleophiles besides to form a range of interesting different products. But with strong concentrated base, the same alkyl bromide may follow an elimination pathway by which HBr is removed from the molecule to form an alkene product, with a preference for the more substituted alkene which is intrinsically more stable. Although changing the base and the size of the base can change the substitution pattern of the alkene product, with this bulky base, the more accessible proton on the end of the molecule is removed in preference to give the less substituted alkene. Meanwhile, alcohols may also be persuaded to undergo elimination reactions via a slightly different mechanism in the presence of strong concentrated acid, which protonates the alcohol, converting OH to H2O, a much better leaving group. We've seen oxidation reactions that increase the oxidation state at carbon from alcohol to aldehyde to carboxylic acid, meaning that primary alcohols, like that at the top here, can be oxidized first to the aldehyde, which is then further oxidized to the carboxylic acid, while secondary alcohols only go as far as the ketone, which has no more hydrogens on the carbon that's bonded to oxygen, and so the reaction stops at this point. We've also talked about the corresponding reduction reactions, which take us from a carboxylic acid or an ester to the aldehyde and down to the primary alcohol. Reagents such as sodium borohydride or lithium aluminium hydride can deliver nucleophilic H- that reacts with an aldehyde or ketone as shown here. While organometallic compounds like these Grignard reagents also add to carbonyl compounds in a carbon-carbon bond forming reaction that is particularly useful in organic synthesis. And finally, we've talked about substitution reactions at acyl centers, like this example where the OH of a carboxylic acid is replaced by Cl, thus converting the acid to the acid chloride. And there are many variations on this theme, from the acid chloride, the acid, the ester, amide or anhydride starting materials, to a range of related products. All in all, we have quite a range of different reactions and reactivity to be thinking about. But focus as much as you can on understanding why things react the way they do. Which reactant has the electrons? Which reactant wants electrons? Which one's a nucleophile? Which one's an electrophile? And then patterns will emerge.